In this video, we'll go over the bisection method for approximating the zero of a function. Now, before we do that, let's remind ourselves of the intermediate value theorem, which allows us to state if there is a zero for a function within a closed interval. Now, the intermediate value theorem states that suppose f is continuous on a closed interval from a to b. Let p be any number between f of a and f of b, so the value of the function at the endpoints of the interval, so that p is either greater than or equal to f of a, less than or equal to f of b, or p is greater than or equal to f of b and less than or equal to f of a. So it means that p is a value between the value of the functions at those endpoints of the closed interval. Then there must exist a number c in this interval from a to b such that f of c is equal to p. Now, often when we talk about the intermediate value theorem, p is equal to 0 and c is a root or a zero of the function. Now, just to remind ourselves of what this means, let's look at a specific example. So let's say if we have the function f of x equals to 3x cubed minus 2x squared minus 2x plus 1. Now, this is a basic example because this function in this case is a polynomial function, and we know that polynomial functions are continuous everywhere, so that so we don't have to worry about the continuity of the function up on the closed interval. But let's say if we want us to show that we know that f of negative 1, that if we plugged in negative 1 into this function, it looks like you get negative 2. F of 0 would be 1. So that means between negative 1 and 0, since one value of the function was negative, the other value was positive, that there must exist a value between negative 1 and 0, such that when you plug it into the function, you get 0, or it's one of the x-intercepts of the function when you look at the graph of the function. And we can see it here, like it looks like it'd be right about here, a little closer to negative 1 than it is to 0, but it is between negative 1 and 0 that we do have this 0 of this function. So that's the intermediate value theorem states that if there exists the 0, or again, another way to say it, or the root of the function, but it doesn't actually find it. Now, what the bisection method is a way to find the 0 once we prove that there is a 0. Now, what we're going to do is, so we know between negative 1 and 0 that there is a 0. So, because we know when we plugged in negative 1 it was negative, and when we plugged in 0 into the function it was positive. Well, let's take the value halfway between negative 1 and 0, which would be negative 1 half, plug that into the function. Well, we know when we plug that into the function, we'd get a positive value. And so that means between negative 1 and negative 1 half, there must be a 0 because, again, negative 1 gave us a negative value. Negative 1 half gave us a positive value. So that means between those two values, there must be a 0. And then what we do is we take that interval, cut that in half, and see what is the value of the function for that. Now let's actually do that, but that's at least what it means graphically. We're going to keep cutting the interval that we know that there exists a 0 for the function in half, so that we could get closer and closer to the actual 0 of the function. So, like I was saying, if we plugged in, let's see, f of negative 1, and again, just a reminder, the function, let's see, f of x was, I think it was 3x cubed minus, let me go back, see what it was, 2x squared minus 2x plus 1, so minus 2x squared minus 2x plus 1. So if we plugged in f of negative 1, or if we plugged in negative 1 into this function, what you'd get it would be negative 2. If we plugged in 0, we got positive 1. So again, by the intermediate value theorem, we don't know that there must exist a 0 in between negative 1 and 0. So we know between negative 1 and 0 there is a 0. So what if we plugged in f of negative 1/2, or that's the same thing as f of, if you want to do it as a decimal, negative 0.5. Or if you did that, you get 1.125. So that must mean, since that's positive, that between negative 1 and negative 0.5, there must be a solution, or a 0, for the function. So what we're going to do is cut that in half. So what we do is plug in this case, that would be negative 3/4 and negative 0.75. And one thing, to find the value which is halfway in between, just a reminder, you add the two values and divide by 2. So negative 1 plus negative 0.5 would be negative 1.5. Divided that by 2, you get negative 0.75. And if you plug that into your calculator, or some other program, maybe like Excel or something, what you get would be positive 0.109375. Now the main thing, it's positive. So remember, when we plugged in negative 1, it was negative. When we plug in negative 0.5, that was positive. Now we plug in the value right in between, it's also positive. That must mean it's the 0 must be between this negative 1 and negative 0.75. Because again, we know it's negative there, positive there. So we find the value halfway in between these two. And again, so what you do is add those two values, divide that by 2. So you get negative 0.875. Plug that into the function, you get negative 0.79102. So that's negative. So we know it's negative in between. So now we must be between this negative 0.875 and the negative 0.75. Because again, it was negative there, positive there. So we got in it a little smaller, and it must be between these two values. So again, find that value halfway in between those. So add those two values, divide by 2. So you get negative 0.8125. Plug that into the function, you get about 0.30444. Which is negative, so it's negative halfway in between. So that must mean it's now between this negative 0.8125 and negative 0.75. So we find the value halfway in between those two. I'm going to just do this a couple more times. I'm not going to do this forever, because you can't just keep going on and on and on. So let's see, negative 0.78125. Plug that into the function. I get negative 0.08871. So it's negative. So now we must be between this negative 0.78125, negative 0.75. So again, that was negative, that was positive. So plugging in the value halfway between there, let's see, so you get negative, let's just do one more, 0.765, 625. Plug that into the function. I get positive 0.12501, so it's now positive. So it must be between this negative 0.78125 and negative 0.765625. So we got really close. So it must be somewhere in between these values. And again, we could keep going on, and what you could do is keep going on until maybe like the first few decimal places will stay the same, and so on and so on. So this is the bisection method. This is a way to better approximate where the zero is actually at. The intermediate value theorem, once again, states the existence of such a zero. The bisection method helps you approximate where the zero is actually at.